Hi guys, in this video we are going to discuss how to find space and time complexities of your code. Our focus will be to find these complexities for the code that you have written during the interview, but this is applicable for any kind of code that you have written in the industry also. Now during the interviews we do not find the time complexity using any equation, right? You must have seen master theorem, master equation, and other things that you have studied during your graduation or post graduation to find the space and time complexities. In our graduation or in our degree, we also talk about multiple ways of computing the space and time complexities. We not only talk about big O, we also talk about small o, we also talk about lambda, we also talk about omega, right? We talk about a lot of symbols, but in the industry we are largely concerned about big O notation. So whenever we say that our code is taking on the order of n time, we are talking about big O complexities, right? We are only concerned about the upper bound. So our focus is going to be that, and in all the data structures in this video, because we want to keep the video short, so we will focus only on questions which are related to arrays. So in array, let's say you have written a problem, let's say you have solved a problem that involves array data structure. So you have written the code, and now you want to find the time complexity of your code. So think about it, that first of all, think about how many times are you traversing the array, how many times are you visiting each element in the array. Next thing is that you should think about what is the time that we are taking at each element, right? So essentially, what is the work done at each element, and obviously how many elements are there. So let's say I want to print the array, and this is code number 1. So I want to write a simple code to print the array. This is a simple for loop where I am traversing each and every element in the array, and there are n elements in the array, and I'm just printing the array. So number 1, the number of elements are n, and we are going to each and every element. And at every element, because we are just printing the element, so we are taking constant time at every element. So the total time taken is n into some constant, which is on the order of n. So this is how we are computing the time complexities. And because the number of variables in this function are constant, right? We have one variable arr, which is an integer pointer, we have one variable n, we have one variable I. So we only have these three variables. So irrespective of the size of the array, the number of variables in this function are going to be constant. So the memory required by this function, or the memory required by the stack frame of this function, does not depend on the input that the function is receiving. So this function takes constant amount of memory irrespective of what the length of the array that is, irrespective of what the value of n is. Now let's take a different function. Let's say I want to write a function. In this function only, let's say I am not printing the element, but I'm checking whether the element is prime number or not. So let's say I want uh, for the given elements in the array, I want to print all the elements in the array which are prime numbers. So let me just change the function. So instead of print array, we will be print prime numbers in the array, right? So we will visit each and every element in the array, and at every element we will check if that element is a prime number or not. So at every element we will check. Let's say we have a function like is prime number. So if is prime number, so if element at I is a prime number, then we will just print it. So now the time complexity, now again we are, first of all, there are n elements in the array, and we are going to each and every element in the array. At every element, what is the work that we are doing? At every element we are computing whether that element is prime number or not. Let's say the computation of it takes on the order of k time to check whether the element is a prime number or not. So the total time taken is on the order of n into k. Now usually in this particular case, checking a prime number depends on the value of the prime number also. So this k in the worst case may be very, very large, because the numbers can be very, very large, right? So this will actually increase the complexity, right? So basically, let us repeat it again. So whenever we want to find the time complexity of the code, we will see how many elements are there in the array, how many times are we visiting each element in the array, and what is the work done at each element, right? In both of these cases, we are visiting element only once, right? Let's take a simple search example. So we are searching for value val in the array using linear search. In this case, we may be visiting the entire array, or we may not be visiting the entire array if we find the value in the earlier elements. So let's say my array is 5 1 3 6 8 9 2, and I'm looking for value 5. So if I'm looking for value 5, then I am actually not traversing the entire array. So this we will only have one in the first iteration of the loop. We will check 5 with, we will compare 5 with ARR of 0, and because both of them are equal, so we will just return from the first iteration of the loop itself, which means that we are not visiting each and every element. So if we are not visiting each and every element, and if we are returning from the first element always, then we will take on the order of one time, right? But this is the best case. In the worst case, we may end up visiting each and every element. Let's say if we are searching for 7, so 7 is not present in the array, and we will be able to conclude whether 7 is not present in the array only by visiting each and every element in the array and comparing that with 7. So first we will go to 5 and then compare it with 7. So 5 is not equal to 7. Move to the next element. 1 is not equal to 7. Move to the next element. 3 is not equal to this 7, and so on. So when this entire for loop is over, then we will move out of the for loop, and from this point we will return false. False indicating that the element is not present in the array. So in this case, we are taking O of n time because we are visiting each and every element, and at each element we are taking constant amount of time, right? So this is the worst case time, or the maximum time. So this is the maximum time that we can take, and this is the minimum time we can take, right? So in these cases, the minimum time and maximum time are different, and this is kind of best case and worst case time complexity. Whereas in the previous case, when we are printing each and every element of the array, there is no best and worst case. We have to visit each and every element, and at each and every element we are taking constant time. So there is only one time complexity. There is no best case and worst case. Whereas in case of searching, there is best case and worst case. Now let's say we are checking if a particular element, for a particular element, let's say we are checking whether the complement of that element is present in the array or not. Let's say the complement is the negative number. So if 5 is present and -5 is also present in the same array, then we will see then we will say that, you know, one pair is present. So we are checking for a pair of positive and negative value of the same type, and we are counting those pairs. So what we will do is that for each element in the array, let's say I have a 5 here. So for each element in the array, I will scan the entire array again and see if -5 is also present in the array. Let's say we have a -8 here. So for this -8, I will scan the entire array and see if 8 is present in the array or not. So basically we are finding the complement of the element in the same array. So we are visiting each element of the array multiple times. If I am at 8, then if I am at 5, then also I will be visiting this -8. If I am at -8, then obviously I am visiting -8. If I am at 3, then also I will be visiting this -8 to check if this element is equal to -3 or not. So here the time complexity will increase because we are visiting each element more than once. So in this is a typical case where the time complexity is O n square, because for each of the n element we are traversing the entire array, and traversing takes O n time. So for each of the element we are taking O n time. So for n elements, we are taking n time, so the total time complexity is O(n) square, right? In all of these cases, we are not considering the recursion. If there is recursion in your code, then recursion will also add to the time and space complexity. So if your code is recursive code, then you need to ask these questions also. How many times is the function called? When I say how many times is the function called, I mean how many times are we calling the function from external functions, as well as how many times the function is calling itself. So this is total number of times the function is called. Then what is the work done by the function? So let's say the function is taking constant time, but the function is called n number of times. So if the function is called n number of times and each time the function is taking constant time, the total time taken is n into some constant, which is on the order of n. Let's say if the function is taking k time, let's say the total work done by the function is k, and the function is called n number of times. So each of the function call will end up taking k time, so the total time taken is n into k. So we say that time taken by this function is on the order of n into k, right? Let's take an example. Let's say I want to print the array recursively. So if I want to print the array recursively, then what I do is, let's say I have an array like 5, 1, 4, 3, 2, 6. So initially there are 6 elements in the array. So ARR is pointing to the first element and total number of elements are 6. Then we say print element at 0, which means print element at 5. So I'm just drawing the stack frames. So initially when the function is called, ARR is pointing to 5 and total number of elements are 6. Then we print the first element, which means we print 5, and we call the function with with pointer pointing to the next element, ARR plus 1, which means that now this ARR is pointing to 1 and n is 5. So it literally means that for this particular function, the array starts from 1 and there are total 5 elements in the array. So this will print the first element of the array, which is 1 for this particular function, and then it will call the function again where the first element is 4 and length of array is also 4. So that will print first element 4, and then it will call the function again where the first element is 3, so that will print 3. Then it will call the function again for where the first element is 2, so it will print 2. Then it will call the function again where the first element is 6, so that will print 6. Then it will call the function again. Now in this last function call, value of n is 0, which means that there are 0 elements in the array. When there are 0 elements in the array, we don't need to do anything and we just return, and all of the functions will return to their calling functions. So if you notice, the total number of function calls in this case are n, and each function is not doing the only work that each function is doing is that it is printing the first element of the array and then calling the other function recursively. So the total work done by each function is some constant. So because each function is taking constant time and there are n instances of the function, so the total time taken is on the order of n. Now interesting thing is that how much memory are we taking? In this case, because there are n instances of the function and each instance of the function takes constant amount of memory, so we end up taking on the order of n extra memory also. This is very important in recursion, because in recursion each stack frame, we don't need to consider, we should not just consider the memory utilization of one instance of the function. So if you look at one instance of this function, then one instance of this function is taking constant memory, because there are only 2 variables in each instance of the function, ARR, which is a pointer to the first element, and n, which is the total number of elements in the array. But the number of instances of the function are large, so each instance is taking constant extra memory, but the function is called multiple times, and because all of those function calls are present in the memory at the same time, So the total consumption by this function, effective consumption by this function, is much higher, which is on the order of n, right? Now let's take one more example. Let's say I have two arrays which are given to me in sorted order, and we want to merge these two arrays in the third array. Let's say the values are 5, 6, 8, 9 and 12, and let's say these are 1, 2, 5, 1, 2, maybe 7, 13, 14 and 20. So the output should be one in the C array. So this is array A, this is array B. In the C array we will have elements of both the arrays in sorted order. Then 12, 13, 14 and 20. If you don't know about the about how to merge two sorted arrays, so you should first look at the algorithm to merge two sorted arrays. In this case, what we are doing is that we are going to each and every element. So we have a pointer to the first element of the first array, we have a pointer to the first element of the second array, and we have a pointer to the first empty position in the third array. We compare the two elements, and whichever is smaller goes to the third array. So we compare 1 and 5. So 1 comes here, and then j is incremented and k is incremented. Now we'll be comparing 2 and 5 because 2 is smaller. So 2 will come here, and then j moves forward. Then we compare 7 and 5. So 5 is smaller, so I moves forward. So whichever element is going to the third array, that pointer is moving forward, because that element is already considered. So 5 has already moved to the final array. So we now need to consider 6. So we compare 6 and 7. 6 is smaller, so 6 comes here and I moves forward. So 7 and 8 are compared. So 7 is smaller, so 7 comes here. K is also moving. K is pointing to the first empty position in the third array, right? I'm not showing K because K is moving irrespective of whether we are moving element from the first array or the second array. So then we compare 8 and 7. So 7 comes here. So after that we compare 8 and 13. So 8 comes here. Then we compare 9 and 13. So 9 is smaller, so 9 comes here. Then we compare 12 and 13. 12 is smaller, so 12 comes here. Now the first array is exhausted. When one of the two arrays is exhausted, we move the leftover elements from the second array to the final array. So because there are three elements which are left in the second array, we move all of these three elements in the final array. Now how do we so there are the first while loop is basically comparing elements from two arrays as long as there are elements in both the arrays. When one of the array is finished, then we move the leftover elements. So the control will either go to this loop or will go to this loop, but not both, right? How do you find time complexities of these kind of functions? So in these kind of functions, rather than looking at how many elements are there and how many elements are not there, we should look at what are the total number of elements that we are touching. So first array A has m elements and second array B has n elements, and we are visiting each element only once. So when one is moved from B to C, after that we are not going to consider one again. So each element is moved, so in each iteration of the loop, exactly one element is moving. So if I consider, let's say that this first while loop has x iteration and this loop has y iteration, then the total number of iterations are x plus y. So I can say that this x plus y will always be equal to m plus n, because in one iteration we are moving one element, and the total number of elements that need to be moved is m plus n. So we are moving all the elements of A and B, total number of elements in A and B are m plus n. In one iteration we are moving exactly one element, so the total number of iterations are going to be x and y. It is possible that this x is equal to m, or x is equal to n, or x is equal to some value. So what will be the value of x and y will depend on the input, but the fact that x plus y number of iterations, sum of the total number of iterations is equal to m plus n will remain true irrespective of what the values are. So we can say that the total time taken is on the order of m plus n, because we are going to m plus n elements and we are performing constant work at those elements by just moving them, right? So each iteration of the loop is taking constant time. Total number of iterations are m plus n, so the total time taken is on the order of m plus n into some constant, and constants are not important, so the total time taken is on the order of m plus n. So in this video we have considered only how to compute the time complexities when the data structure is array. In the next video maybe we will consider how to compute the time complexities of linked list questions, and how to compute the time complexities of binary tree and graph data structures, which is very interesting because in case of binary trees the solution is usually recursive. Please subscribe to our channel so that you can get notifications whenever those kind of videos will come. All right, I hope this is useful. Thank you.